your audio.
I got it. Okay, I got it. Okay, should we start or should we wait a few more minutes?
We'll start, and we are recording. We'd like to thank you for coming. And as a recognition of your contribution to our educational endeavor, we will give $100 to the Presidential Scholarship. And we will send you a letter denoting this. Thank you so much.
Thank you. Thank you. So let's start then. So everybody can see my screen now?
Yes.
Okay, good.
Not yet.
Not yet.
Not yet?
One last button, share screen.
Not
You got
yet.
to select which screen to share.
Okay. How about now?
Very good. Yes.
You got
That
it. Go to
looks good.
presentation mode. That's it.
Okay. Thank you, everyone. So let's start with this project Super Collider. And it's between 1989 and 1993. And I was in this project for 4 years as a design engineer. So I would like to talk about this. It's about 480 slides. So I have a 2-hour time, and I'm hoping that it would be enough. So as you can see, what Nikola Tesla said. So with that, I would like to talk about these two individuals. Dr. Roy Schwitters was the head of the Super Collider, or the director of Super Collider, between 1989 and 94. On the right-hand side was a very special man, Jerry Toole. He passed away, unfortunately, 2 years ago. He was my manager. He was the director of the accelerator, or the head of the accelerator division. And prior to Super Collider, he came from Fermilab. And he was at Fermilab about 25 years. He just retired in the final steps of this 1993 when Super Collider was in real trouble. This is the beginning. November of 1989, when I was just hired at the Super Collider, and this is where the initial buildings were put together. That was in the south of Dallas, and in fact, it's about 35 miles north of Waxahachie, where the Super Collider was eventually to be built. From the very beginning, in 1983, there was a effort at the University of California, Berkeley, trying to put together the design concepts. And finally, in 1993, when the Super Collider was canceled due to, from the US Congress, it was one of the biggest programs that was in the United States, and its preeminence in scientific discovery. If it would have been built, sure. So this is one of the billboards, or one of the boards in the final days of the Super Collider, and it said, a dream that never happened. October 21, 93, US Congress decided overwhelmingly to kill the SSC project. And what remained of that for over 20 years after the 93 was a vacant lot with a lot of buildings and lots of investment. If it had gone according to the plan, this particle accelerator would have discovered the Higgs boson, or Higgs particle. And Peter Higgs, who was the eventual Nobel Prize winner in 2012, would have had his Nobel Prize a lot sooner. In fact, if this was built, there was no need to build LHC, or Large Hadron Collider, in Switzerland. It would have been irrelevant. Let's watch this video from CERN or LHC.
You're looking at a collision between two protons, accelerated to almost the speed of light. The energy of the colliding protons produces hundreds of new particles. Such collisions may help physicists understand basic constituents of matter and the fundamental laws of the universe. To make such collisions, CERN built the world's largest machine, the Large Hadron Collider, or LHC. This particle accelerator lies 100 meters below the French and Swiss countryside, with collisions taking place at 4 points around its ring. We are now in the Large Hadron Collider's tunnel, where 9,000 magnets are used to bend and focus two beams of particles. Here they are, running in opposite directions. And here is CMS, one of the 4 particle detectors which surround the collision points. More than 1 billion particle collisions occur each second at the heart of CMS, which works like a huge digital camera taking 3D snapshots of these collisions. CMS is a huge machine, nearly twice as heavy as the Eiffel Tower. Like a cylindrical onion, CMS is made up of lots of subdetectors that identify the type and measure the trajectory and energy of the particles which fly out of the collisions. Collected data may show us new phenomena and is vital to help answer some of the most exciting questions about our universe. In 2012, it helped prove the existence of the Higgs boson, the never-before-seen particle that explains why matter has mass.
How did the video come? Everything is going fine?
The video looked like it was for 3D and or some sort of VR glasses, none of which I have. But other than that, it was sort of interpretable.
Okay. So these are some of the papers, newspapers that I've still kept them to this very day. October '93, when finally the Super Collider project was voted to be canceled. In fact, during that period, as you can see in this, 20% of the laboratory was completed. 54-mile tunnel that was to be eventually part of the largest collider ever built. You can see what is shaded in black. These were already been completed, and some magnets, in fact, were installed in the underground. It was such an important project that we had presidents and many important people visiting often. Here you see President Herbert Walker Bush and also Dr. Roy Schwitters, director of the laboratory. And what is shown in here is a part of this half sector, 5 quadrupole and 5 dipole and 1 quadrupole superconducting magnets. Of course, it was an election year. Towards the end of 1992, Democrats and Republicans both were running, and President Clinton also was in full support of the project. So when the collider finally was canceled, every newspaper in the country, and in fact, even in Europe, there were all headlines as such: is there life after collider? And the picture that you see in here is showing some of the construction sites where this is linear accelerator tunnel. It's the first accelerator in the part of these chain of the boosters that was part of the Super Collider. When everything's said and done, Metroplex, so-called the Dallas newspaper, were saying that what really took place and how it will impact the economy of southern Texas. So these are continuing on, and every article, every newspaper, every TV station, there was something in the evening news about this Super Collider. It began in 1983 with a conceptual design. And how it started was President Ronald Reagan was in full support. And he, in fact, in 1986, 2 years before, you see in this slide, he gathered 4 of the Nobel Prize winners, the American Nobel Prize winners in the White House. And I'm going to play a video briefly showing that what was the reason that this thing happened. So let's watch this thing. And I'll only play maybe a few minutes of it. It's a very long video.
Please be seated. Mr. President and distinguished guests, and Mr. President, these are distinguished guests. Getting 4 American Nobel Prize winners on the stage at one time, I think, is quite an accomplishment. Dr. Cronin, Dr. Weinberg, Dr. Ting, and Dr. Richter. Ladies and gentlemen, a year ago, the President made the decision to move ahead with the construction in the United States of the world's largest and most powerful high-energy accelerator, the Super Collider. The President weighed the budgetary, the economic, and the scientific arguments and decided for America's future. Our scientific future, our future technology, our future competitiveness as a nation, and yes, our educational future, as demonstrated by these outstanding honor students in science from across the country who are with us here today and on this stage. Now, this outcome came as no surprise to those of us who have had the great honor of serving Ronald Reagan, an historic president. The President's basic instinct on any issue has always been to look ahead and to resist the temptations to do what is expedient today, to create a vision of tomorrow for the United States and for the world. Today, in the face of ever-increasing, tougher global competition, the importance of the Super Collider is all the more critical to our nation's future. The accomplishments of the Nobel laureates on this stage and the promise of these high school and college honors science students who are with us this morning says much about where this nation is today and where we can go if we continue to chart the right course.
I'm going to move it a little ahead.
Eminence in high energy physics. I believe that we can make the super presentation to the President.
This is Dr. Weinberg, a Nobel Prize winner in physics.
Mr. President, last year you decided to proceed with the construction of the Superconducting Super Collider. This decision was a major milestone in the support of basic scientific research by your administration, and we wish to congratulate you on the wisdom of this decision. The SSC would be the latest in a sequence of particle accelerators. The first, the cyclotron, was built by Ernest Lawrence in 1930 in Berkeley. The SSC is the next step needed to make progress in this field. It represents America's commitment to the pursuit of excellence in basic scientific research. It's also a commitment to our nation's next generation of young scientists. Today you have before you in the audience a group of some of the brightest members of this next generation. I hope they don't all go into high-energy physics because we need some of them to do other useful things, perhaps in the 21st century being President of the United States. They'll need the SSC, those of them who go into physics, to make progress at the scientific and technological frontiers that they'll have to explore. If we don't build it here in this country, then they're all going to have to get on planes and go off to Switzerland or Japan or the Soviet Union to do their experiments.
Okay, so the video could be watched as this is recorded for later on. It's a long one. So we want to take a look at universe and what is making universe. This is where macro physics, large physics meets microphysics. Two branch of advanced theoretical physics talks about cosmology and elementary particles. There is a great connection between these two areas in physics. What we call universe is space and time, and everything that is inside it, all the planets, all the stars, galaxies, and every form of matter and energy. There's a well understood theory of the Big Bang that it describes the cosmological description of the universe. How did the universe begin? There are very large numbers here that I'm going to be talking about, and they are billions and trillions, just to show that 9 0 and 12 0 for each. The first thing that comes to mind to ask, how large is our universe? It's 94 billion years. That's a very large number. That's about 22 0 in front of this number. So to me, that's infinite. Some of these units that are really used in cosmology, one of them, for example, astronomical unit, that's about 63,000 astronomical unit in 1 light year. So when you're talking 94 billion light years, it's unimaginable how large this place is. So it's safe to say universe is infinite, and we are part of the universe. And also universe is very cold. In fact, 2.7 degree Kelvin, that's almost close to absolute zero. That gives you in Fahrenheit how cold this place is. Once Einstein said that universe and humanity, they have one characteristic, they are stupidity. And in fact, universe is not one of them. Pretty good. So what is the origin of life? It's an eternal question. It could be answered by religion. It could be answered to some extent by science. We ask ourselves, where did they come from? Why are we here? Where are we going? These are few questions and few answers that I'm hoping that we can capture tonight. Some of these numbers, how old is our universe? Again, numbers are very large, 13.7 billion years. When we think about billion years, I don't know what to say about this. I can only imagine the number of years that I have in my, advanced age. So 13.7 billion years, that's a long time. And there are a lot of galaxies inside this universe that we call world. 20 trillion, that's a very large number. And Hubble telescope has already discovered 100 billion of this. So we have come a long way. And our Earth is located in a Milky Way galaxy. And how old is this Milky Way galaxy? Very large number again, 13.61 billion years. And the place that we live, the only planet that life exists, is 4.5 billion years. So these numbers, they make you think. Once there was a great man, Leon Lederman. I'm not sure that everybody has heard of him, but he won Nobel Prize. He was a director of Fermilab. And he's been known that he called the Higgs boson one of the things that accelerators were struggling to find. He called it God particle. And we have to understand that a little bit later. So Leon Lederman was the director of Fermilab, unfortunately passed away in 2018, lived a good life. And here it is at Fermilab. So as the director of Fermilab, he supported the idea of building Super Collider. He was definitely one of the key people that in the central design group was suggesting that an accelerator of the size of the Super Collider is needed. He wrote the book, The God Particle. The question that he asked if the universe is answer, what is the question? Very thinkable statement. But later on, he clarified, the God that I'm using is not a theological God. It's a metaphorically, basically, philosophical terms. He said, nature is very complex. We have to understand it. Leon Lederman quit Fermilab at the peak of his scientific work after winning Nobel Prize and decided to go and teach preschool kids. And the reason for that was he wanted to see the world again once more from these child's eyes, so unclouded eyes. Children are very interesting. They can ask all kinds of questions. In fact, before the children are grown up, they go to school and they get educated by older people. They've been told how to ask, how to think. But prior to that, they are innocent and they ask very interesting questions. They ask fundamental questions. Here you see Leon Lederman on the left with his kids. These kids are from some types of preschoolers or maybe kindergarten. And he's teaching them, he's asking questions and he's answering them. And he claimed that he learned a lot from little kids. So since humans have been curious about the world, they have been trying to answer two basic questions. What are things made of? How do they work? These are really very fundamental and very important questions. To find answer for this type of questions, we have been able to find some answers over the years, over the decades, especially in 20th century. And accelerators are a big part of it. What happened in 1970s and 80s, there was significant progress in using particle accelerators and sensitive detectors to find some of the answer to questions of the elementary particles and the forces that hold these elementary particles together. However, some of the deeper questions still remained, and it required some energy levels much higher than what was available. In mid-80s, there was a particle accelerator called Tevatron, 1 TeV, tera electron volt, and at Fermilab outside Chicago. And it really was significant. Many, many new particles were discovered there, but still we were not there. We wanted to have a much better answer for some of these fundamental questions. So the relationship again goes back to this Big Bang theory. What happened at the beginning of time and space? And to get there, we needed more energy. So starting in 1984, a group of exceptional scientists and engineers, they decided that there is a need to build a very superior machine called Super Collider to be 20 times more energetic than Fermilab or Tevatron. SSC, or Superconducting Super Collider, as we know, if it would have been built, it would answer some of these questions for something in the size of a billionth of billions. That's 10 to the power of 24 of an inch. So we really shrink into space now. We're going into this singularity of space. Also the time. We want to go back in time. Everything is revolving around the time then when everything was right at the beginning of this Big Bang. And the time that happened, as I mentioned in the previous slide, it was a billion years ago, 13, 14 billion years ago. Could you please mute that audio? Somebody is actually, I hear this noise in the background. Yeah, so we have been always curious, and the progress that we have been able to make is continuing on, and it will continue for the unseeable future. That's the nature of us. We always are seeking to find answers. So some of these basic questions again, what is the ultimate structure of matter? What is matter made of? What are the forces that hold these small particles or matter together? And how do they interact with each other? How did the universe begin? Will it ever end? Here is another image that you see President Bush and also director of the laboratory, Secretary of Energy, and some other politicians. These are, I think, representatives from Texas, visiting this super collider string test, as we called it. It was half a cell. And this is a year that was very decisive. It was an election year. And so all these politicians were beginning to lobby for big projects. And Super Collider was one of the 3 top ticket programs at the time: a space station, a stealth bomber, and Super Collider. These were highly visible projects. So let's watch this video, a short visit that's happening with President Bush.
This past Tuesday. Just ahead on Road to the White House, remarks by President Bush. On Thursday, he traveled to Dallas, Texas for a tour of the Superconducting Super Collider facility. On Monday, the Senate is scheduled to debate an appropriations bill totaling $550 million to keep the research project going. A spending bill in the House was defeated last month.
The miracle, and we'll show you, sir, where we build the magnets. The miracle of superconductivity is that we can take electrical current that you can barely see down on the end. You see big bars of copper coming in. And we can reduce that down to a fine wire and run it through here. But without that technology, you could never build this accelerator. So that's been our push. In fact, Alan has challenged us from the beginning to make sure that we can build these magnets properly. I think what we're going to do is,
How much of this do we have?
this is what we call a half sector of the half cell of a machine. But this represents the simplest reproducible unit. So we have 100 yards of it right now here, hooked up, cold, superconducting. In fact, we put current through it. We put 1,000 amperes through it last night, Alan.
Yep.
And this, as I say, will just be reproduced. When we go around that tunnel, we'll just take another one of these and another one and another one. 54 miles. 54 miles. Yeah.
The president then headed to Southern California for a series of campaign-related events. In addition to several private fundraisers, Mr. Bush spoke to workers at Odetics Incorporated, located in Orange County. Just ahead, highlights of the president's Thursday afternoon campaign appearance this past Tuesday.
So the history of universe, as physicists modeled it as Big Bang. This is the beginning, the Big Bang taking place. This is the origin of time and space. So they claim that it began 13.7 billion, close to that number. And as the universe, the time passed, the universe started expanding. Initially, the expansion rate was not that steep, but in recent times, the expansion has become much steeper. And there are a lot of theories about this, and this is where we are at the moment, and this is the future. So we call this point singularity. This is where space and time is zero. This is the terminology that physicists use. 7.5 billion years later, the expansion rate is increasing in here, so the slope is much faster right now. So at this stage, objects are flying all over the place at a much faster rate. Astronomers are having a theory believing that there are dark forces pushing these galaxies farther and farther apart. If this is the beginning, this is where the Big Bang taking place, and you're moving in this axis on this time and evolution of our universe, and the coordinates of this expansion of the time is showing that the black force energy is residing up here. It's understood that in the first microsecond, there was only particle physics. In the earliest moments of the universe, there were no atoms, no nuclei, no proton, no electron, no neutron, nothing. In the earliest moments of the universe, only elementary particles interacting through elementary forces. Again, the word is elementary particles and fundamental forces. What are they? At the beginning, everything was unified. There is a theory that Einstein spent majority of his life, I guess, towards the end, especially in unification theory, claiming that the gravity and all these other forces that I'm going to speak about tonight were one. Everything started with one force. So it was assumed that, understood at least, that gravity and strong interaction, weak interaction, and electromagnetic interaction, they were one field. I'm going to skip this slide and go back to take some of the basic thinking of Stephen Hawking. And this is a very 1-minute video. Let's watch this one.
Which came first, the chicken or the egg? Did the universe have a beginning, and if so, what happened before then? Where did the universe come from, and where is it going?
His questions are very fundamental and important for us to think about what happened at the beginning. Is the universe, did it have it at the beginning? And what happened before that, if there was a beginning? Where did it come from, and where is it going?
How real is time? Will it ever come to an end? Where does the difference between the past and the future come from? Why do we remember the past, but not the future?
So if you take this approach to where SSC is with respect to very large and very small, 10 to the power of 24, 10 to the power of minus 20, talking about orders of magnitude. Galileo said here, all these cosmological events are taking place in here when we are looking deep into sky and trying to understand the nature of forces and the objects billions and billions of years away. And in here, with the Super Collider, we would have been looking at very small, the tiniest objects, the tiniest elementary particles, and their lifespan and the physical properties associated with that. This is where we are. This is where we are trying to be and trying to understand at both ends of this space and time, how things began. It's the map of this Super Collider location. Dallas up here, and we are about 30 miles south of city of Dallas. About half an hour drive, you get to this place where the small town Waxahachie resides. Super Collider major ring would have been, this thing is shown in here, and there are a number of other accelerators also prior to this large collider. It's located in Texas, of course. So the question comes up, why do you need this size of a particle accelerator. Why is it necessary? 87.1 kilometers is a very large space. And we will answer that tonight, hopefully. So initially in phase one, inside these 4 accelerators, linear accelerator, low energy booster, medium energy booster, and high energy booster. Protons are starting from basically speed of 0, and they accelerate gradually until they are fed inside this large collider. There are 2 sets of magnets, or 2 sets of rings, ring 1, ring 2. Protons, the charged particles, they move in opposite direction at a very high speed, and they collide. And during the collision, we are looking for elementary particles. So if we imagine this is the ring of the collider, the particles are moving in this ring at a very high speed, almost 0.9999, as close to the speed of light as possible. This is the cross section of the tunnel with 2 sets of magnets. And here we have these interaction regions. And in here, we take the beam into these detectors and collide them. And when the collision takes place, minute particles of very small physical size, they come out of this, and the physicists study these particles to understand the elementary particles and the forces that hold these particles together.
In October 1993, the U.S.
one.
Congress terminated the Superconducting Super Collider when its estimated price tag went above $10 billion. The SSC was designed to do a pretty wide range of physics goals, but at the very core of it was to find the Higgs boson. And ever since, this project has been referred to as a watershed in the history of science, or history of physics especially, in that the funding for high-energy physics was either flat or declining ever since.
Inside Science.
One day, Director Emeritus of SLAC, Wolfgang Panofsky, best known as PIEF, came into my office and he said, "You know, I think this was a bridge too far." And I always often puzzled what that meant, and finally resolved it years later when I realized that this was the title of a book about a disastrous Allied campaign during World War II. But that really keyed my thinking about this project. The SSC was designed to understand, why do particles have mass? And, the theories generally had massless particles in them, and they had a high degree of symmetry. And you had to break that symmetry down by giving particles mass. And there was a mechanism called the Higgs mechanism that did this in a very natural way. But it required the existence of a particle called the Higgs boson. And nobody could really specify the mass it had to have. There was a large range of masses, ranging from, about the mass of a proton up to about 1,000 times the mass of a proton, in which it might occur. And so successive particle colliders and accelerators went looking for this. The SSC was built to be sure that they could either find the Higgs boson or find some other phenomenon responsible for why particles have mass. The SSC was understood that it would have to be a multi-billion-dollar project. Everything the community had done before that had been hundreds of millions of dollars, say evaluated in $1990. This one was clearly going to be 2, 3, and eventually was over $10 billion. When you get to those kinds of numbers, you have to bring in partners. In this case, the Texas politicos, members of the military-industrial complex. To them, it was a high-tech jobs project. And that was the image that they projected in Congress. And that is like the kiss of death, right? Especially when you have a multi-billion-dollar project that is growing seemingly out of control, pressing on many other projects, not just science projects, but also water projects in various districts throughout the nation. Was this project too big for the U.S. high-energy physics community to embrace? And in general, I think it was. The SSC was indeed a bridge too far.
So particle accelerators create the condition immediately after the Big Bang. That's in a simple way to. So what was SSC? SSC had 4 accelerator before this, called the collider. It started with LINAC, very small in length compared to a collider, 148 meter. The energy of the particle, which is proton in this case, goes from 0 to 0.6 GeV. That's giga electron volt. And electron volt is a unit of energy. We don't measure it in joules when we deal with particles. And from there, we go into this LEB, low energy booster. And these guys, they do have regular magnet, 540 meter, and it's a circular and boost energy to 11 GeV. Next, we go into medium energy booster, still regular magnet, 33.96 kilometers in circumference, takes energy up to 200 GeV. HEB, high energy booster, is a superconductor ring, and it's about 10.69 kilometers, and it reaches to 2 TeV, or tera electron volt. And finally, it feeds the collider, which is the largest, 87 kilometer, and each beam would be moving at 20 TeV. Collision will happen at 40 TeV, two opposing beam coming at 20 TeV at each other. So why not use a fixed target collision? Fixed target implies that you do have only one direction particle coming and hitting the target. When you do that, it's a problem of yield. With 20 TeV, you're only going to get about 2/10 of a TeV useful collision. The rest is just going to go into debris and waste. So therefore, colliding from coming in opposite direction beam of 20 TeV will give you the maximum yield. And that's where you want to be. You want to generate the largest, I guess, collision and answer some of these questions. So the question comes up again, why is 81 kilometer? This is wrong, it should be 81 kilometer. It's due to the fact that every charged particle, when it moves in a nonlinear direction, in a curve or curvature space, they will create radiation, and we call that synchrotron radiation. It's electromagnetic radiation, the same as it would be in antennas for those of us in the EMC field. And by the way, also 87 kilometers or 81 kilometers, it's got a very gentle curve. So it would be radiation, synchronous radiation still will be there, but it will be very small. So we can get the maximum energy out of these collisions. Here, this is a modeling tool that's basically been used at DAISY by Igor, and then he's showing that a charged particle, when it's taking the path of this curvature, there is electromagnetic radiation, and that's what we call synchrotron radiation. In another simulation, the charged particle is moving around this circular path, which would be what we will have in LEB, high energy booster, and you can see that you create radiation. So this will happen. You cannot really avoid this, but if the curvature is not so steep, maybe the radiation extent would not be as bad. The energy of the proton, of course, would reach the 20 TeV or tera electron volt. Very large number of protons will fill the ring, 130 trillion, and it will be 100 million collisions per second. Not all the protons will actually result into elementary particle when they collide. There are a lot of magnets in here. That's the major part of the cost of the projects like this. 4,326 dipole magnets. And these, I'm talking about superconducting magnets. And each magnet about 15.8 meter long, very large structures, and they weigh a lot, 5,000 kilograms. Next set of magnets, we call them quadrupole magnets, and about over 1,000 of them. And they're slightly smaller than the dipole magnets and slightly lighter. The main ring, again, is going to be 87.1 kilometers. And total number of magnets, including this, what we call a special purpose magnet, those are for correction purposes, about 12,000. The iron weight is about 44,000 tons. And you're going to use a lot of cables in here, superconducting cables, to build this magnet. That's about 25,000 kilometers. Compare that with the circumference of Earth. So it's almost just like almost going around the Earth. These magnets are superconducting, so they have to be cooled. And they use liquid nitrogen and liquid helium, the two layers of cryogenics, to cool these magnets so they can achieve the superconducting state. I don't know how much of this video we want to watch, so let's just see.
We took giant leaps toward exploring the vastness of the universe.
14 years after the moon landing, plans formed for an equally ambitious American adventure to study atoms.
Crossing this frontier is the mission of high-energy physics and the function of particle accelerators, some of the world's most advanced scientific instruments.
But most people outside of North Texas, and even many here today, have never heard of it.
The Superconducting Super Collider.
Joe Bohr doesn't like to pull out this map, or the suitcase of Superconducting Super Collider, or SSC memorabilia, that he's kept stored away like old baseball cards, but never looks at.
Here you are. Here's Waxahachie.
Bohr was one of the world's leading tunneling experts when he was picked as the construction manager for the SSC's above-ground buildings and the 54-mile tunnel that would house the Super Collider's ring.
This would have been the world's largest underground project.
And when this tunnel boring machine has completed its task, it, along with more than 5 similar machines, will have chewed a 54-mile oval ring under the Texas countryside.
The irony of the massive scale is that its goal was to study the tiniest particles in the universe.
My cliche is what the world is made of and how the pieces work.
Roy Schwitters left a professorship as a physicist at Harvard and moved to Texas in 1989 after being tapped as the top man in charge of the SSC.
It was a big step, but it was doable.
Animation from the Super Collider at CERN in Switzerland shows how it works, spinning part of an atom called protons around a tube at the speed of light. When they crash into each other, scientists are able to study reactions that haven't happened since the Big Bang.
The Superconducting Super Collider is the doorway to that new world of quantum change.
It really was a dream project.
Edwin Farrow was on Waxahachie City Council and part of the group lobbying to bring home the SSC and its promise of 8,000 jobs.
It's something that would really elevate our educational system.
Finally, this big project came to town.
Ellis County Judge Todd Little was just 18 when the project finally got approved in 1987.
I think that scientists would have poured into this region from all over the world. We were going to be creating energy by smashing atoms.
Waxahachie won because it sits on a bed of limestone, perfect for tunneling.
We set world records in tunneling on this job.
In 10 months, machines dug 16 miles of the project that would have been 3 times larger than the one now in Switzerland, twice as big as the Channel, and 10 miles larger than Dallas's Loop 12. Criticism began even before construction started in 1991. A 1 centimeter change in the SSC's tube upped the price by $1 billion. By 1992, the cost had gone from $3 billion to 10.
So we will get behind this new president and wish him well.
And a Texas president had lost the election.
Clinton came on and didn't support it, period. It was just that.
Thank you very much, Mr. Chairman.
New lawmakers with no connection to the project were willing to drop it.
The cost of the Super Collider are too high, and the benefits to Americans are too uncertain.
Keeps rising from the dead to suck up budget dollars.
How are we going to afford it? How are we going to pay for it?
In October of 1993, with $2 billion spent and 2,000 people working on it,
I cannot continue support for the SSC.
Congress finally killed the SSC.
Yeah, our biggest concern was that it wouldn't, that Waxahachie itself would just fold up. When it left. The shale is easy to cut.
Bohr kept digging till the last dollar ran out in 1994, hoping something would change. Bohr stayed, but it would be 4 years before he could bring himself to visit the site.
I have to blank it out of my mind because it persists. I keep thinking about it. What could have been?
The tunnels have been flooded with water, the shafts are capped, and the buildings now house a chemical manufacturer.
What comes to my mind is opportunity lost.
Switzerland's Super Collider was eventually finished in 2008 and is responsible for multiple Nobel Prizes, attracts 120,000 visitors a year, and is home to 70% of the world's particle physicists.
We'd have them coming to Waxahachie. So how much is that worth to you?
And that's something you just can't go out and buy that.
It's an unknown history to many and a buried memory for those who almost changed the world.
We'll never know what could have been.
Okay, so let's just do a comparison between what is LHC, Large Hadron Collider in Switzerland, and Super Collider. LHC uses 2 beams of protons at combined energy of 13 TeV compared with 40 TeV for Super Collider. Cost of building LHC has been $4.1 billion compared with $11 billion of 1994 of the SSC. It would have been equivalent to $18 billion today. It took about 14 years to build LHC, and Super Collider would have been completed in 10 years. In fact, by 1999, it would have been commissioned. Circumference of LHC is only 27 kilometers compared to 87.1 kilometers for Super Collider. They are able to achieve much higher magnetic field in LHC 8.3 Tesla compared to 6.5 Tesla at Super Collider. This doesn't surprise me because technology has improved with the superconducting cables. LHC uses far less magnets than Super Collider. Of course, we have 2 rings. We have to multiply this by 2. So that adds to the cost of the Super Collider to be a lot higher than LHC. Luminosity, I will define luminosity in a few slides ahead. That's really like a density of the particles. LHC is about 10 times higher than what Super Collider. The higher this number is, the better it is for collision and for discovery of elementary particles. Inductance of the dipole magnets for LHC is 110 millihenry and 75 millihenry for Super Collider. So that's just number here. LHC can handle 13,000 ampere, 13 kiloampere compared to 7 kiloampere of the Super Collider. So that also will tell you are able to squeeze these protons together and steer them a lot better than what we would have been able to do at the Super Collider. The cryogenic operating temperature at LHC is 1.9 degree Kelvin compared to 44.2 Kelvin at Super Collider. So we were operating at a warmer temperatures. The higher the current goes, you need to have this temperature lowered. The power consumption for LHC is about 200 megawatts. That's equivalent to 1/3 of what would be used in the city of Geneva. Super Collider would have demanded significantly higher power, 900 megawatt. And that's just because of the large number of magnets, 8 times larger number of magnets. So the name of the game is, again, going to the smallest particle. And we understand today that quarks are the building blocks of nature. So you want to probe into this, and you need these particle accelerators. Today's we hear about the past 2-3 years about this virus, COVID-19. It's really not that small. It's about 100 nanometer. So I've heard people talking being about a nanometer, but that's what really has been reported by Scientific American, about 100 nanometer. Quark is significantly smaller, 10 to the power of minus 18. 10 to the power of minus 7, so several orders of magnitude smaller. We are trying to find this. If we start on the top from the virus and of 100 nanometer in diameter, we go 100 times smaller, we get into molecules, and this is molecules of water, about 10 to the power of minus 9 meter in diameter. Still go further down, we get into these atoms. Atoms are 10 times smaller than the simplest molecules found in nature. So we are going to regime of 10 to the power of minus 10 meter. Still, we go further down, 10,000 times smaller, we get into the nucleus of the atom, 10 to the power of minus 14. And these are not stories, these have been known, and they have been known for a long time. Then we dig deeper, 10 times lower, we get into the protons and neutrons inside the nucleus of this atom. And these are made of small particles, and they are called quark. U stands for up quark, D for down quark. And they're held together by some forces. These forces are very strong indeed. And the dimension that we're talking in here is about 10 to the power of minus 15 for proton. Then 1,000 times smaller, you get to quark. Now we are into 10 to the power of minus 18. And the question remains, is there anything smaller than quark? That to be found maybe in decades ahead. But at least the idea is to be able to isolate and find or detect the quark, if that's ever possible. Quarks are fundamental, as fundamental as it can be. We say that everything is built of quarks and is labeled with what we call hadrons. And hadron basically is a number of quarks put together, and they're held together by this very strong force, one of the 4 forces of nature. Quark, in fact, was the name quark came from this very fascinating man, Mary Gilman. I met this person back at the Super Collider in 1991. He was an MIT physicist that won the Nobel Prize in 1969, and he made a model for the quark. They call it Gilman quark model. And he just sadly died about 3 years ago. Hadron basically is a subatomic particle or composite that makes these protons and neutrons. And so you put 3 quarks to make a proton and 3 quarks make a neutron. And they're held together by this force we call a strong force, a strong attraction. Now we want to probe again further into this nature. Not that long ago, 100 years ago, people were searching to find the model of an atom. And Niels Bohr quantized it, or made this, picture of this atom with electrons going in these curved paths, and then quantize that thing. So how many electrons you can have in a given shell, and how far apart they are from each other, and what holds them in place. After that, Rutherford in England made the model, simple model of the atom, and it was very simplistic. This is before the birth of quantum physics. That is, electrons were moving around in the form of a cloud around this nucleus of the atom. But this did not really last that long. And then many further knowledge came along in the 20th century, the mass of electron and mass of the proton. All these were measured, but it's important to realize the ratio in here. This proton is about 2,000 times heavier than electron. These numbers are really insane, right? 10 to the power of minus 31, 10 to the power of minus 27. What are these things really? Even the accuracy that they state, these so many decimal points. But they have established facts. These are been tested. So we needed a new physics or new mechanics to explain these very small particles and their interactions. And that could not be explained by classical mechanics. So they came and created this quantum physics or quantum mechanics and wave function. And this is a famous Schrodinger's equation. And this describes the motion of a very small particle of a mass m moving in a one-dimensional space, x being one dimension. So this wave function is a function of space and time. When the particle is moving in an environment that has a potential of v, which again, function of space and time, h being the Planck's constant. So what does it really mean? If you want to compare the classical with quantum mechanics, if you have this red being a ball or some object is held by spring to this point. The physical location of this object can easily be described mathematically, and observations are not very difficult. You can detect it and locate the position at a given time. However, in quantum mechanics, things get really very complex. For example, these 6 diagrams that you see in here is representing the likelihood of finding the particle as it is oscillating. So we call this so-called this harmonic oscillation. On the image C, this is so-called the time invariant, or so the likelihood of the particle being spatially, this X is the space and this is the location. So it's going to basically swing between these two. But when there is a time element in here, picture D through H, it becomes very difficult. This wave function solution has got real and imaginary parts. So just wanted to hint that this quantum mechanics is not that trivial, it's not that simple. It's talking about a special wave. It's not we're not dealing with these ordinary waves in the sense that our community in electromagnetics or EMC is used to think of. So let's watch this one.
In an unchanging universe, one can imagine that God created the universe at literally any time in the past. On the other hand, if the universe is expanding, there may be physical reasons why there had to be a beginning. An expanding universe does not preclude a creator, but it does place limits on when he might have carried out his job.
All right, so to build an accelerator, you need superconducting magnets. Superconducting magnets, they do two things. They take these proton beams and they steer them. They steer them around these oval paths. Magnetic field, we know that interacts with charged particles, and protons are charged particles. So one thing that comes into mind that the quality of this field that is generated by these magnets, that is very important, and much of the progress made in the 1990s was improve the quality of this field, so without any ripple. Dipoles, as it says, it has 2 poles. It creates a uniform vertical field, and that bends the proton beam. Each dipole in the super collider was supposed to be 15.8 meter, so it bends the beam in a very small angle, and that helps to reduce the synchrotron radiation. Quadrupole, as the name says, it has 4 poles, and is used to focus the beam. It's just like lens, like optical lens. For every 5 dipole, there was 1 quadrupole, and so that is really will be shown in the picture in a moment. So once the protons are accelerated to the fullest energy, being 20 TeV, the design was to make it to the beam to stay for 2 days, traveling more or less like 180 time round trip to sun back to Earth, and to confine this thing into a very, very small area, like a few millimeter. So there are also, in addition to these dipoles and quadrupole magnets, there are specialized magnets there. These are periodically inserted inside this ring, just to correct any type of misalignment or any imperfection that may be happening. Interaction region, that's where the collisions take place. They do have very special magnets. Some of them are used to squeeze the beam even tighter and steer them towards the collision. And these magnets are very special, and in a sense that they take the beam luminosity, even make it smaller from millimeter into micrometer. And the detectors of the colliders are located in these interaction regions. This is an image that I have captured from the SSC dipole and quadrupole. And you can see that it's brown, as shown in here. These are the superconducting cables. They're wound on a core, which is made of copper, and they're held together by stainless steel. Image of the dipole and a quadrupole in here. LHC, designed and developed like 20 years later, and they made improvements. They put 2 beam pipes inside the same magnet. So this is now helping a great deal in reduction of the cost and also the size of this machine. So Collider would have had 1 beam pipe, so we needed a stack of 2 rings, whereas LHC has only 1. Another thing was the aperture, or the inner diameter of the SSD was 50 millimeter. LHC is slightly bigger by 6 millimeter, not a big deal. An image again at our magnet development laboratory at Brookhaven National Lab. This is where some of the magnets were developed at early stage of Super Collider. Here they're inspecting the magnets and they're assembling the magnets. Another image showing at Fermilab where these magnets are tested for the field quality. So they apply power and they are already in the cryogenic temperature at about 4 degrees Kelvin. And they look for the quality of magnetic field generated in these. United States has not lost the edge in terms of accelerators and magnet technology. In fact, all the magnets, majority of the high-end magnets are designed and developed in the United States, and mostly at BNL or Brookhaven National Lab. This one shows, for example, for LHC, the field distribution of the dual aperture magnets. And finally, the magnet is sent to LHC. You can see 2 beam pipes in here, one going in this direction, one in opposite direction, and they are doing the cryogenic testing. By cryogenics, I mean they insert the liquid nitrogen and liquid helium, and they cool these superconducting magnets to operational condition. Here, that a magnet is inserted in the tunnel. You can see 2 beam pipes within the same magnet assembly. And initially, it was designed to operate at 362 megajoules, and this is a very large energy. But in 2012, when the Higgs boson was discovered at LHC, they only had 145 megajoules of energy inside this. These are the images that I had captured. This is from the Super Collider. Again, you can see that they were stacked up 2 rings, and these are dipole magnets. Further down, it shows the cross-section of these magnets, and another picture will show you better. Okay, you can see that this is where the liquid helium is moving, and this is liquid nitrogen. Liquid helium is very, very low temperature. In fact, the transition temperature to become liquid is around 4 degrees Kelvin. Liquid nitrogen is much higher. There are all types of insulation, thermal insulation between these. So the ultimate goal here is to keep this part of the magnet at very low temperature so you can achieve superconductivity. And a much finer picture here, you can see the core, copper. Copper, by the way, doesn't have any type of magnetic properties in terms of being able to alter or change the magnetic field generated by these cables. So the cables are these flat cables wrapped around the core, and everything held together by this stainless steel. The same magnet just at the Fermilab and Tevatron accelerator just a couple of years before they were Super Collider projects kicked in. And the same magnets are designed at LBL laboratory or sent to CERN. And this is the one, just notice there is the 1 ring in here. Let's take a look at a brief video of what's going on at LHC. As you can see, most of these magnets are designed here at national labs in the United States. So one of the greatest technological improvement in recent time has been moving around from niobium titanium to niobium tin. These are capable of generating magnetic field as high as 12 Tesla. That's like double of what it was possible at the Super Collider at the time, 30 years ago. And that's roughly about 250,000 times stronger than what would be Earth's magnetic field. These will be installed at in 2 years' time at LHC, and they will double the luminosity or the strength of this field. This image shows how they lower the magnet into the tunnel. This is the access shaft, and we had 4 of these built at the Super Collider back in 1990. Here you see the magnet has been transported the tunnel. The quality of the LHC dipole magnet, this has been modeled here with numerical tools. I'm going to skip some of these videos if they're not really related to the topic that I'm talking about. The limitation of time I'm watching is about 45 minutes, so I have to move on. So what happens with the superconducting magnet? There is one issue called quench. And what is quench? Quench means basically if it happens, it will destroy the magnet. It will be the end of magnet. These magnets are extremely expensive. At the time, at the Super Collider, they're talking about $50 million per magnet. And at the early stage, probably would have come down later. So they're not very cheap. So quench basically implies something, but we have to understand that before getting into what quench means, magnets are capable of storing significantly large energy. In fact, if that happens, then during the quench, this energy would be dumped into this magnetic winding, the coil winding, and it will create intense heat, and that will destroy the magnet. And helium, by the way, has less affinity to be a liquid. It likes to be a gas. And technology to keep it at this low temperature and making it liquid, called cryogenics, is very, very complex. And as far as the cables, we are really good these days. We can make 100,000 kilometers per year. So production of these cables have improved in terms of. So let me talk about this stored magnetic energy. Magnetic energy density could be calculated magnetic flux squared divided by permeability of the air, because the core in here being copper is the same as air as far as the magnetic properties are concerned. And 6.3 Tesla was the magnetic field flux at Super Collider. That would result in 1.58 times 10 to the power of 7 joule per cubic meter. SSC collider dipole energy would have been 1/2 Li squared. The normal 75 millihenry was the inductance of the dipole magnet. And at 7,000 ampere, it will result 1.84 megajoules. Now, what does it really mean? If we take this magnet, which I mentioned in slides before, dipole is a 5,000 kilogram mass. And we say that all this electric energy, electromagnetic energy, is converted to kinetic energy. That will result into a 61 miles an hour or 97, 98 kilometers per hour. That implies basically that magnet, the energy stored in each one of these magnets, equivalent to a truck like this, a 450, coming at 98 kilometers an hour or 61 miles an hour towards you. So this is the type of energy that we're dealing suddenly will be unleashed inside this dipole magnet if quench happens. So how does the quench take place? If we represent this inductor, this is the superconducting magnet, is powered from a very high current power supply, but extremely low voltage, typically about 20 to 25 volts. But the current capability of this power supply is very high. At the time, it was 7,000 ampere for SSC. For LHC, they claim is about 13,000 ampere. In some part of this coil, a region starts becoming resistive. And there are many reasons for that, but if I had time, I will describe that maybe towards the end. When that happens, then we call that event quench. So superconducting magnet develop resistance. And then that energy, that's basically now the large current flowing through this small resistor. The resistors may be milliohms at the beginning, but you can anticipate with 7,000 ampere at the collider, the heat that generated by a few milliohm of resistance would be significant. So now this resistance will start growing, and the other parts of this coil will become resistive. When that happens, the voltage drop across that resistor is measurable. It can be actually much, much larger than the supply voltage. I was responsible for designing some of the electronics for detection of the quench. The quench starts growing in 3 dimensions. It moves in horizontal and also in vertical, like in 3 dimensions. And then this happens very, very rapidly. When this takes place, it doesn't take much time for the magnet temperature to rise. In fact, we're about 200 milliseconds. Now we're reaching almost the room temperature. Remember, these magnets are immersed in liquid helium. That's around about 3 to 4 degrees Kelvin. So within 200 milliseconds, that entire magnet is sitting at room temperature. We have liquid helium inside this magnet. Liquid helium expands very rapidly. And the ratio of the gas to liquid helium is very large. It's like 6 orders of magnitude or so. So then the magnet will explode. And the power that we dealt with, that I showed with the truck at 61 miles per hour, that is the amount of force this magnet will experience. So now to measure this, there's a special circuitry, but so we detect this quench very rapidly. And when that's detected, for some of us, we use this concept of load dump in automotive sector. It is a load dump resistor. This is a massive resistor that can absorb all the energy. So there is a switch that gets activated. They open the switch from the main power supply. And this loop is now completed. So now the resistor goes in parallel with the superconducting magnet, and all that energy is dissipated in this resistor. These resistors are like old office cubicles, very high power megawatt type resistors. And the time constant for this dissipation to happen for the super collider was 36 seconds. So it exponentially decays in this thing at 36-second time constant. Now, while this is taking place, there are special resistors built inside this superconducting magnet. We try to make it thermally, make the magnet go into thermal equivalence of basically balancing the temperature between one end to the other end. This helps the magnet to recover from this quench before going into destruction. In recent time, they have used a lot more new technology. They put in sensors, and in fact, at LHC, they're putting as many as 3,000 sensors to detect the quench. You really want to protect these magnets. It's just not one magnet. Basically, if one of them goes quenches, the entire ring may go. And that is basically probably 70–80% of the cost of the particle accelerator. Again, I'm going to, yeah, this one shows, for example, at a very simple, this is not a magnet, it's just the cryogenics. Once the cryogenics start expanding, very high pressure leaves the magnet. Of course, this is not a magnet. I don't have a quenching magnet video. It's literally impossible. This is under the ground. And as late as 2008, there was a quench event that took place at CERN and destroyed a number of magnets. They're talking about hundreds of millions of euros of damage what happened, and shut the machine down for 2 years. So I'm going to skip these videos again. These are all from Stephen Hawking, but time is very limited, so I need to go through these very quickly. There's a term that I used previously, I call luminosity. What is luminosity? Luminosity is given by this relationship. Basically, it is the number of events divided by time and inversely proportional cross section. But really, this really fancy way of saying is the number of protons in a cross section of the beam divided by time. So how fast this beam or particle and how dense it is. That's what it really is. So pictorially, if this is the bunch of protons, cross section of this is basically measured from one end to the other end, and the number of protons that fit inside this oval shape, red oval shape, is the luminosity. So the luminosity of the Super Collider 33 years ago was designed to achieve 10 to the power of 33 centimeters square per second. And at that time, we expected to have 2,800 bunches per beam. And each one of these bunches carried about 10 to the power of 11 protons per bunch. And they all moved at this non-relativistic, just slightly below the speed of light, 0.9999 times speed of light. And with a dimensions of 10 micrometer in diameter of the beam at the collision, that will result into this type of energy, 1 gigajoules per beam. So what does that really mean? Somebody asked, if you put your hand in front of this proton beam coming at the SSC, what would happen? Somebody characterized that back then, it would be like sitting in front of this guy. And you don't want that. It will just go through you and it will just vaporize you. So a little bit about superconductivity. The technology at the time was niobium, titanium, and alloy. Superconductors are a special material. Their electrical resistance goes to 0 at some low temperature. And they have an ability to repel this magnetic flux. And that has a lot of industrial applications. Superconductors, they can maintain current with no voltage applied across this superconducting cable. The experiments have shown that they can persist for decades, for a long time. In fact, some have claimed that actually in an ideal situation, it can go up to 100,000 years. That's almost unimaginable. So low temperature superconductivity, that's what we are talking about, happens at temperatures below 4.2 degree Kelvin. And when that happens, resistivity goes to 0. In this picture, I'm showing if you have a piece of metal and you keep lowering the temperature going in this direction, at some point the resistance basically becomes as small as it can, but it never goes to 0. Whereas in red, I show that the superconducting cable, it drops in resistance, and suddenly at some temperature, which we call critical temperature, it drops instantly to 0. And this is where you want to be when you're operating these magnets. In 3 dimensions, magnetic flux density, temperature, and current density. It shows that when niobium titanium, this comes from one of our documents back from the Super Collider. So this image shows the cross section of the niobium titanium embedded in this lattice of copper, giving a scale or feeling for what we're dealing with. And superconducting cable again with the substrate of copper. And this picture was taken when, years later after the superconducting magnets were still in the tunnel, and somebody must have broken and taken these pictures. And another picture showing these niobium titanium wires at LHC machines. So I'm going to skip that. So what is particle accelerator? Particle accelerator, this is Fermilab. I'm just going to show this thing briefly. I think it's about a minute. Let's watch this thing. As you can see, the same idea was to be at the Super Collider. You have a linear accelerator, you go through a booster, and eventually you go to the main ring, and collision takes place at some point. So early days, in fact, everyone had these. I still have one of these. is a CRT cathode ray tube TV. This is basically a particle accelerator also. You have an ion source, electrons. You go through these special magnetic coils that on the neck of the picture tube, and these are bending or steering the beam of the electron that goes up and down, and this is where the monitor is, and you apply very large static voltage here, and that is an acceleration so that you form image. And this is a particle accelerator with an RF source, and these are resonant cavities where the red circles are the beam of protons are moving and getting energy from the generator, which is located here. There are about 30,000 accelerators in the world, but they are all very low power compared to what we consider for LHC. So cyclotron was built in 1939. It's still, I think, is there. Van de Graaff generator in 1960s. At DAISY, they have the synchrotron electron accelerator. At Brookhaven National Laboratory, this is relativistic heavy ion collider. So this is a fixed target collider. At Lawrence Livermore National Lab, this is in California. An image in Oak Ridge National Lab. This is a neutral neutron, doesn't have any charge. So there's another accelerator there. Stanford Linear Accelerator at Palo Alto and Stanford University. This is electron positron accelerator. And this is a detector at the Fermilab Tevatron. Tevatron was shut down about 12 years ago, by the way. It is because CERN is now overtaken the higher energy collision, so there's no need to run the Tevatron. And this is LHC, or Larger Hadron Collider at CERN. I pass this. There are a lot of videos in here. I will try to provide this presentation to Scott Lytle later. You can probably put it in the website if you want to watch these things. So the RF cavities are utilized to provide energy for the beam, so to accelerate the particles. So particles of protons, they come in a bunch, and there is a gap between these bunches. And we know that whenever you have electric field, charged particle in presence of electric field will experience force, and that will basically make the protons move. In here, we are seeing the proton bunch, and the gap, this gap actually is several meters, and these bunches are less than half a meter. And I will bypass this video. This just shows the electric field. And these are, by the way, RF, very high frequency, about 400 megahertz. And that causes the particle to move and then get into this resonant cavity. This is where we apply the RF to provide energy to propel the electrons. Okay, this one shows the current LHC resonant cavity. This is a superconducting resonant cavity. And it works like so. So you have the charged particles, the protons, and you have this RF signal that's going through this resonant cavity and operating at 400 megahertz. And that's how it gives energy to proton to accelerate. You will never get to the speed of light, but you will get very close to it, like almost like 0.9999 speed of light. That's what the concept was. So here, next picture shows the this RF system for giving energy to the proton beam. This is the resonant cavity here, and the blue and red is emulating the field there. And you can see that red small bunch of protons, when they reach that resonant cavity, they gain energy and they move on. And there are many of them. I don't know exactly at LHC, but at the Super Collider, every 50 magnets apart, there was one klystron tube that created this energy that's needed for this resonant cavity. All right, so next one. But klystrons are extremely high power RF amplifiers. These are capable of megawatts and megavolts of operational capability, and these are used to basically provide energy for propelling protons. A couple of quick slides on detectors. These are two images of the detector that were in the development stage for the Super Collider. So this is the picture. I think it was Fermilab. They were building this. Again, the picture shows this is from 1989. And they are very complex, and they are used. Basically, these are the cameras for detecting the images. I pass this. Get to the more interesting stuff. So the forces that holds these elementary particles together, what are they? We call them again elementary or fundamental forces. If you look at this picture, there's a lot to say, but I want to emphasize everything in here in the next few slides. Interactions or the forces are they called weak interaction, strong interaction, electromagnetic, and gravitation. This is all we know today. Has been known for a long time, for the past 50 years or so. Everybody knows about gravitation, and gravitational force is what holds things together in a planetary and us on Earth. But then these numbers is comparing the relative to the gravitation. If you take a look at the strong force on here, and 10 to the power 38 times more powerful than gravitational force. However, it is proportional, it's so-called the long distance behavior. This is meant for very, very small, short distances, 10 to the power minus 15. That's basically what we call femtometer in terms of measurement. Beyond that, it actually loses its meaning. This is the force that holds these quarks together, and they are held together by a particle, and those particles are called gluons. And you will see that in the next few slides. Hopefully I have enough energy to describe this phenomenon. This is the most interesting part of elementary particle physics. Now, in electromagnetics, we think about these mediating particles. We call them photons. That is these particles that basically makes the light move from one point to another. And again, in terms of its strength, relative strength, is much, much stronger than gravitational forces. So gravitational force is not really that strong, but it matters because its range is infinite. And the weak interaction, so this is also very large. If you can look at these three and compare them to Earth, it gives you, to gravitation, gives you an idea about what we are dealing with. So in the following slides, I'll go and elaborate on this thing. So strong interaction, we said, is 100 times stronger than electromagnetic. And I'm bringing this first because we're all in this EMC community here in automotive EMC. But it is 10 to 13 times stronger than weak interaction, and 10 to the power 38 times as strong as gravitation. Now, we take a look at this strong interaction. That is the force that's basically holding the protons together inside the nucleus. Nucleus of an atom, the protons should repel each other because they do have same charge, but they don't, because there is this other force that comes into picture, and that's this strong force. And the range of that force is, again, 1 femtometer. So it is it's an attractive force, and it basically overcomes the electromagnetic force, which is repelling. Like charges should repel. Electrostatic force will tell you that. But the range of the distance, again, 10 to the power minus 15 or femtometer. But after a little, slightly more than that, 2.5 femtometer, it loses its efficiency, or it's not even important anymore. In fact, at distances much, much smaller than 1 femtometer, like 0.75, it becomes repulsive. And that's the reason that it gives dimension to the nucleus. Otherwise, one could have assumed why the nucleus of an atom is not 0, it's not smaller than what it is. Now, on strong forces, there's this exchange particle. There's another elementary particle that is basically used to hold these particles together, meaning quarks and stuff like so. So it is very similar to photon, which is used as a particle for electromagnetic interactions. They all have mass electric charge, and a spin. When I talk about the spin in here, we have to be careful. This is a quantum mechanical term. It's not the orbital spin as we are, in the classical terms. Mass is measured, and mass is basically zero for gluon, but it's really experimentally has been shown to be less than 1.3 MeV per c squared. If I have enough time, I will describe what these units are, because this is we don't measure things in gram, in joule. We measure them in EV, and MeV per c squared will be explained very briefly. So the strong forces are basically using this mass mediator, which we call gluon. If you look at this table, there's a chart in here. It has everything, and I will try to describe it. So elementary particles are shown on this side of the table, and the forces or interaction forces are shown on this side, with the exception of this interesting particle, which we call Higgs boson. The particles can be classified in this quadrant or here, and the first quadrant are called quarks. Quarks could be up or down, charm or strange, top and bottom. These terms, they all have certain meaning, but everything that you and I are made of, everything that we find in nature are in this generation 1, which is from this side. And there's another family of the elementary particles, we call them leptons. An electron, for example, that we're all familiar with is a lepton. They all have mass, they have charge, and they have a spin. Everything that in elementary particle physics has to be having some mass, charge, or spin. Some of them, they may have zero charge or zero mass. We will see that. But what is peculiar about this quarks, as shown in here, by the way, quarks were discovered in a SLAC, Stanford Linear Accelerator, in 1968. As you can see, in here they do have charge of an integer, odd integer, and also they have a half spin. Whereas the mass of these quarks, and here you can see that they increase rapidly. When you go from the generation 1 to generation 2 to generation 3, you're going from MeV to GeV and higher. So these two are the one that makes everything that we have in nature. The rest of them are found in particle accelerator or in cosmic radiation. Next, there are again 6 types of quarks. Quarks cannot exist in isolation. And the reason for that is the phenomena we call color confinement in physics. So quarks, all of them, they have spin of half. Up quark has got a charge of 2/3 of E. E is the charge on electron. Down quark has a charge of -1/3 of E. All right. Ordinary matter that the universe consists of is made of generation 1. It's made of these guys. So if everything is made of from up and down quarks, what is inside the neutron and proton? Everything that we know of in our existing life is made of protons and neutrons. So proton has got 2 up quarks and 1 down quarks. Neutron has got 2 down quarks, 1 up quarks. Now, if we do a little bit of a calculation, we know we're trying to find the mass and the charge. And if we add all the properties that are known in that table, we find out the charge of a proton is 1 electron, or the plus opposite charge of an electron. The mass of the proton, if I do the calculation, it works out to be 9.1 MeV, but it's not 9.1, it is 938.27. So what is wrong in here? And that is this thing here. These charges that are holding these individual quarks together, they have also mass associated with them. And the mass of these particles, these so-called gluons, have to be added to account for that. So these are, again, all very interesting things. And also with neutron, the same thing. You have 2 down quarks, 1 up quarks. And if you do the math, you find the charge is equal to 0, but the mass, again, is much lower than what is measurable, and that's because of the, if we do not account for these gluons that hold this together. All right, so type 2 and 3 are not easily available, at least they're not available in real life, and they have to be found in with high energy collisions in particle accelerator. Some properties about them, they all have a spin of type 1, but they are much heavier, as I mentioned. And you can easily see it again in this table. The number starts increasing. All right, so the forces that hold these quarks and leptons together are classified in the right-hand side of the table. Again, for strong forces, there are gluon. For exchange particles, there are photons. And for boson and Z boson and W boson, as they're called, they're used for weak forces. Here in this picture, you can see inside the neutron and proton, and you can see the role of the gluon. These small circles are the gluon, the interaction or interacting or the mediating forces or mediating particles. It's extremely interesting that, you know, these particles, this is happening all the time, and that is basically a short range. Again, the distance inside the nucleus of an atom between protons and neutrons, we are talking in terms of 1 femtometer, 10 to the power of minus 15 meter. And these are all have been observed, they have been discovered, they have been detected in these particle accelerators. Electromagnetic interaction, we are all familiar in this EMC community with that. These are these electromagnetic forces that they, you know, the force that's acting between electric and magnetic objects. So we have been told that these electromagnetic forces are carried by electromagnetic fields, meaning electric and magnetic field. They're responsible for radiation, electromagnetic, such as light. A quick example of the charged particles, which we call electromagnetic, they obey this classical relationship that the charge between the objects and also inverse proportionality, the distance between these two. Something to note in here, 1 coulomb is a very, very large charge. If you have that in reality, if that's ever possible, you put them 1 millimeter apart, the force that would be the repulsion force between these two charged particles will amount to 10 to the power of 16 Newton. And that's enough force to lift all the millions of Empire State buildings or all the buildings in the United States simultaneously. We know that 1 coulomb does not exist. It's extremely large. But again, if you take a 4 kilogram of water, basically 1 gallon of water, and put it in a container, and it will have about 200 million coulombs of charge. And if you put 2 of these buckets next to each other, the force that you're going to have will be about 10 to the power of minus 26. That's 10 times more powerful or more stronger than the weight of the Earth due to its own gravitational force. Gravitational forces or interactions are given by this classical equation. Again, there's an inverse square law here, and so-called Newton's constant or the gravitational constant. Now, on the weak interaction, that is what's responsible for radioactive beta decay. This is what causes a neutron to decay into proton, electron, and antineutrino. And that happens at a very high speed, almost speed of light, 2.9 times 10 to the power of 8. However, the free neutrons, it takes about 15 minutes for it to decay, and that's the problem in nuclear reactors and causes radiation problem. However, once the neutrons are inside the atom in the nucleus, they are stable. Nothing will ever happen. That's due to those strong forces. It shows the free electron decay, free neutron decay again, going into proton, electron, and antineutrino. Also, there are other particles, we call them muon and tau, and they also decay, and also neutrino. Neutrino is an interesting particle. It has almost mass of 0. you can take a look at this number. This is very small. It has no charge, no mass. If you think about it for a moment, that if there's a particle with no charge, no mass, but it has a spin, but it's also an important particle that has been detected in nuclear reactor, and also is an antimatter of this beta decay. Muon is much heavier particle, but also it has a weak force. But look at the time constants in here. The neutrino is highly durable. It will last 100 million years. However, muon, it would disappear in microsecond. It's got a very short life. Now, the W and Z bosons, these are these forces, the particles that basically are responsible for weak force or weak interaction. But they are so massive, so they cannot travel very fast. And they decay very, very quickly. And we saw that in 1 microsecond, it's almost over. At short distances like this, you need to think about things in terms of quantum physics. We cannot really imagine or even try to explain this in terms of classical mechanics. WZ boson, which are the mediator of this weak interaction, they have, again, mass of 80 G per second, and they have electron, boson, W boson and Z boson, they have the opposite charge, and they have a spin of 1. Again, they are very, very short-lived. You can see 10 to the power of minus 25 seconds. All of these were discovered at CERN in Geneva in 1984, and that gave Nobel Prize for Carlo Rubbia and Simon Van Dier. Okay, in putting it together, you can see that the quark in here, 2 up quarks and down quark, and you can see the neutron, and you can see the proton, just replacing the down and up quark. You see the role of electron, which is a lepton, and the size of an atom. All these numbers, they are putting together the way that our universe, our atom, or the elementary particles come together. And each one of these atoms makes us, makes the objects around us, makes the matter around us. So they call these force carriers or the messenger particles. And so they are these theory behind this thing, which we call quantum field theory, to be able to explain how they actually exist. So Richard Feynman, a very famous physicist, Nobel Prize winner, created this very nice diagram. They're known in quantum mechanics as Feynman diagram. The area of that, if you're looking for this, is quantum electrodynamics. And sadly, he died about just after the Challenger accident in 1989, I believe he died. So in this picture, you can see that interaction between 2 electrons, and this mediator particle in here is the photon, this is shown as gamma, and here just as there are 2 ways to explain this thing. So it says that each particle has a field associated with that, and the field that's generated by one could be, I guess, felt by the other one. So that's one way of thinking about it. Another one is basically this, they call this virtual particle in here. So that basically there is a scattering of the electrons. So if I have time, maybe I've got 10 minutes, I have to go pretty quickly. Candice, can you tell me, are we supposed to finish at 7:15, or can you go slightly longer?
Oh, you can go longer.
Okay, I'm trying as best as possible because the story is very interesting, but unfortunately time limitation and my energy level. So, all right, so let's go. I will skip this slide. This is basically summing everything. Again, skipping video. So one of the unification, everybody has been struggling in the so-called high energy physics to explain the unification, meaning that right at the beginning of time, when the Big Bang happened, all the forces, they were one. And then somehow years later, when I talk in years, I'm talking about billions of years later, they became 4 forces. And so Maxwell was able to, and Faraday and Maxwell contributed to that, were able to get the electric and magnetic fields, and they said they are really the same thing. one makes the other, and they are related spatially and temporally. So from a spatial variation of one is a time variation of the other. So these are clearly indicating that we are almost in a very, very small part of the world of this universe, trying to understand electromagnetics. But so his contribution is this, and of course they both result into electromagnetic waves. And I'm going to skip this one. Again, here we have quarks, we have leptons, and these are the force carriers. Now, this is the interesting part that we call the Higgs boson. And hopefully I will have time to explain this, because that's really the highlight of this my talk today. So let me skip these. This has always been a question for physicists and for engineers. Action felt at a distance. So when we have two objects at some distance, spatially I'm talking about, apart, and without coming in contact with each other, physically touching each other, what is going on in here? How do they interact with each other? So it goes back to the same thing that I mentioned earlier. It's all about unification of everything. One major, I guess, contribution was due to these three people. Steven Weinberg, that we saw next to President Reagan in 1988, talking in the Rose Garden about the Super Collider. And Sheldon Glashow, he's a Harvard professor, he's still alive, but sadly, Steven Weinberg just died a couple of years ago. And Abdus Salam was at Imperial College London, and they contributed to the unification of weak and electromagnetic interaction. This is right now solid. This is not a shakable theory. They have been able to unify weak interaction and electromagnetic. And that's a major, major thing, achievement. In they got this 1979 Nobel, but I think their work is far more than what just a single Nobel Prize winner. So again, Steven Weinberg, that he just died last year, and he was at the University of Texas towards the end of his life at Austin. And Abdus Salam at the Imperial College, and of course, he died a long time ago. Let me see if this video is of interest.
One evening.
So we will pass this one. So now we get into this interesting part, Higgs boson or Higgs particle. That finally is, they used to call it elusive particle or God particle by Leon Lederman. Finally, in 2012, Peter Higgs got his Nobel Prize for this idea. So this is 40 years in making. So Super Collider would have made this thing possible, I would say, by the year 2002, 2003. So he would have got his Nobel. So back then, we said that Hubble, in 1929, he had an idea. He said that the distant galaxies are showing that there is actually moving faster away from us, and that's due to this redshift phenomenon. What is redshift phenomenon? So Doppler redshift occurs when light source moves away from you. When it comes towards you, it is blue. When it goes away, it becomes red. And in here from ESA, European Space Agency, I have a short video. I'll show you this phenomenon. It's very nice. You can see this is optical beam, and depends on your observation point. You can see where it's turning red on the left and blue on the right-hand side. That just shows that if the light source or the electromagnetic source is moving away from you, this is so-called apparent wavelength, is changing the color. So because of that alone, this basically told us that these galaxies are moving away and moving very fast from us. So the universe is expanding. So this idea of a Big Bang, which emanated in 1927, it told us that the universe was very small, almost like a dot, like a singular point, like nanometer. And it was very hot, it was dense, and that was like 13.7 billion years. Don't ask me why. In 1998, not that long ago, two physicists, astronomers at Berkeley, California, they made an observation of supernova. those are exploding stars, that they were moving from Earth at an accelerating rate, and that gave them a Nobel Prize in 2011. Physicists had made an assumption that this matter in this universe eventually would slow down its expansion, and gravity would take over and will bring it back to where it was. It will basically shrink. So in the first moments, again, it was very hot and very dense. As the universe cooled, and we said that it was about average temperature is about 4 degrees Kelvin, a condition became just right to give rise to building block of matters. So the quarks and electrons were created or made. In the first moment, universe was hot again. Back to it. I'm going to slide these things and come back to this if I have maybe after 7:50 some time to outline this. So we said there are 4 forces in nature, and there is no 5th one. Nobody has spoken or even made a theory about this. These are electromagnetic, weak, strong, and gravitation. Electromagnetic forces and weak interaction already been unified. That is what gave the Steven Weinberg and Sheldon and also the Abdul Salam Nobel Prize. So this has already been verified. Now, gravitational interaction is very complex. We don't really fully understand it as much as it is felt and experienced, but we don't really fully understand. Strong interactions are well understood, and I gave a lot of examples. So there's a model in physics we call a standard model. Standard model is really the model for particle physics. It basically tells you that these 3 forces are known as fundamental forces, excluding gravity. I said briefly that photons carry electromagnetic interaction, W and Z boson carry weak interaction, and gluons carry strong interaction. And I'm going to skip that one. And I spoke about this one, forces, enough of this until I get to this. Okay. All right, so what is interaction via exchange particle? Imagine you have 2 objects. One is sitting on the boat, another one here. There is a ball here, and they're trying to interact, these 2 with each other. So C is the exchange particle. A throws the C, and C moves. Nothing is happening to B yet until the B receives it. And when it receives it, B moves to the right. So now B has experienced the impact of A. And we all know if we are doing this electromagnetic simulations, especially with tools like CST, we have seen that field doesn't move instantaneously. It takes time to move from point A to point B. So not that B has experienced the point B, not B takes the ball and throws it towards it. As he does that, and then he starts moving further up. So this is the interacting force. It's a very simple, very, I guess, a naive way of describing what is going on between between matter A and matter B, or the elementary particle A and elementary particle B. So let's bypass this one. Now, very quickly, I mentioned that mass is measured in MeV per c squared, energy in MeV, and momentum is measured in MeV per c. Why? These are basically some units. Mass energy equivalence, this is due to Einstein, it's equal mc squared. We know that mass can be therefore be E over c squared. E is measured in electron volt, so therefore it makes sense to measure mass in electron volt per c squared. M stands for mega, basically is a larger unit. So therefore, the mass of the electron, charge of electron, mass of the electron. And we take an example here. We take a mosquito, and I claim that mosquito has got an energy of 1.5 TeV. Why is that? Because mosquito measures about 2 milligrams, and it moves at approximately 1 to 1.5 miles per hour. That's about 0.5 meter per second. It has small kinetic energy, and if you convert this by the equation that I gave earlier, it works out 1.56 TeV. Indeed, this TeV, and we are talking about moving protons at 20 TeV at the Super Collider. Therefore, this mosquito has, but the mosquito has got a very large size. It consists of billions and billions of atoms. So we cannot, of course, expect the collision between two mosquitoes to be as dramatic as the collision at the Super Collider or LHC. So if you take every particle that starts accelerating at the speed of light, its mass is going to change. And so M0 we call rest mass when the proton is sitting at stationary, and that has been known. And if we consider that into this Einstein relationship, the mass of the rest energy mass of the proton works out to be about 938 MeV. And now if the proton is moving at a high speed as it is moving in the particle accelerator, 0.99c, and we basically apply the Lorentz correction factor for the mass, and we find out that the mass of the proton at relativistic speed, almost at the collision, is about 1 TeV. Yeah, it's just a table of just for those who want to look at it later on. Okay, photon is an interesting particle. It's a particle that has no mass, it has no charge. And this is used actually for electromagnetic interaction. Since it has no mass, it can move at a velocity of light. This is basically according to special theory of relativity, that nothing can move faster than light, but photon is actually the particle of light. All right, so I think I'm getting there right now. So when the Big Bang happened, right at the beginning, something interesting took place. So the question in here is, if the elementary particle did not have mass, and what do we mean by elementary particles? Electrons, photons, and quarks. Let's say they don't have any mass. The universe that you and I come from and live would be meaningless, would be very different than the way it is. And I'm showing in MeV here the mass. Now, if that was the case, if they did not have mass, electrons and protons will not be trapped together, will not be actually creating an atom. You need to have mass to actually have an atom. And how does that become about? So there would be no hydrogen atom, no star, no galaxy, no life if there was no mass in the elementary particles. So after the Big Bang, or immediately after the Big Bang, there was no mass associated with any of these particles. I'm showing this up, and all the quarks and everything, all the force carriers and here, everything, zero. But we understand that at some point, immediately after the Big Bang, all these particles, they started getting some mass. Some didn't, but most of them did. And that's basically due to some idea that came about from these two, and of course, Peter Higgs on the top of all that. So they proposed there is such a thing as Higgs particle. What did they propose? They proposed immediately after the Big Bang, a force field was created or came into action. All these particles, up, down, and photons, electrons, they have zero mass, as shown in here. Zero mass. Now they start interacting with this field, and they start gaining mass, as we can see here. And that mass increases the more interaction they have. However, some special particles like photon, they don't get any mass. They're not affected by this Higgs field. They call this thing Higgs field. But what is Higgs field? We know about this electromagnetic field. We know if we take an inductor connected to a supply, and we have an electron moving on a piece of wire, the magnetic field generated by this loop in here will have an impact on this direction of the flow of the charge. We know this one. And also, we know that if you have a light bulb that creates electromagnetic particle, it will create this photons or gamma or the quantum particles. But can you manipulate or can you change this Higgs field? Well, in order to do that, we need quantum particle or Higgs boson. If we don't have Higgs boson, we will not be having this Higgs field. To create that thing, we must be able to use this event that took place immediately after the Big Bang. So one way to do this thing is using particle accelerator. And that's what Super Collider was built to do that. It was pretty hot idea of early 80s that we needed to discover, at least to see if the theoretical physicists were, right in terms of predicting this Higgs particle. At high energy, that can happen. And of course, Super Collider failed. It didn't happen. And at LHC, they were able to, this is LHC ring, and these are all the detectors. So Higgs bosons were detected, but Higgs boson is also very unstable. It immediately decays and transforms into possibly 4 electrons or 2 gamma particles, and so on. This is the place, this is the detectors used at in July 2012. It resulted into discovery of the Higgs boson. And these are some images. And it gave the Nobel Prize in 2013. Yeah. So what is so special about this Higgs field? We all know there are 2 kinds of fields in nature. We know we have vector field, like wind, and like electric field, magnetic field, gravitation. And we now have a scalar field. Scalar field like temperature, like voltage, they don't have any direction. These have direction, these only have magnitude. Now, quantum particle associated with vector field has also an quantum spin, like shown in here. Like a photon has no mass, has no charge, but it has a spin. Higgs boson doesn't have any spin, doesn't have any angular momentum. So that is what's unique about it, and they call it elusive particle, something that particle accelerator like Tevatron are not able to. That was the motivation behind the Super Collider, to build a Super Collider. So cosmic rays, the beam of the highly energetic particles that in the outer space that they hit Earth's atmosphere, they originate from sun or from solar system in our own galaxy. They are extremely powerful. In fact, they're far more than what any particle accelerator that we can build. Look at this number. It is 21 million times more energetic than LHC and 7 million times more than what Super Collider would have been. One quick thing, the current that we feed to these magnets are not like they're really strange, and they do have this ramp up, ramp down, until we reach the so-called operational. So typically at CERN, I know it is at Super Collider, it's about 7 hours, but this current profile is taken from the LHC operating condition. These are some pictures. I go very quickly of our Super Collider days. This is again the pictures I took, some of them, and some of them colleagues gave me. But I want to also mention that at LHC, at CERN, in 2020, they have reached 6.8 TeV. This is a video. I don't have enough time to really show you this thing, but it's taken a long time to reach 6.8. Super Collider at the year 1999 was capable, or at least was forecasted to be capable of generating 20 TeV. And so a lot more of discoveries would have happened if the Super Collider would have become real. So this is our magnet development lab. Was where they were designing and building these magnets. This is one of the collider magnets, actually dipole magnet. This is a boring machine for the tunnel. These are, as I mentioned, there were 2 rings. So, that's what made the Super Collider so expensive. This is the tunnel access. So we already had this shaft that drilled into the ground. These are some of the SSC complexes in the year 2003. This shows the Tevatron lab with the first superconducting magnet to be tested. This was in early 80s. This is what is the year 2003. That's what happened to this laboratory where presidents and high-level people will walk in. This was completely everything was stolen and taken out of this place. I don't think anybody was really aware of what was going on. So I will skip this video. This is showing that how the tunnel was bored and back in July 93. Some of the buildings in 10 years after the Super Collider was shut down. And again, some images of what happened to the LINAC. Again, some of the buildings there. Very quickly, again, construction of the tunnel and some of the people operating this, large machines, etc. And then some part of the tunnel again. This is Tevatron at Fermilab. It is 1 pi mile in circumference. This is LHC detector, LHC ring, and boring machine in action, and RF cavities at CERN. So as of October 92, this was what really has been done. LINAC design was complete and construction started in June 92. LEB was complete in design and started in December of 92 construction. MEB was complete and design started in June of 93, and test beams 60% complete and so on. So this was the status report at the time when everything was decided to abort the program. So this is a shot at this test that we did back in August of 92. And we ramped the current to 6,800 ampere here. This is the string test that I showed the picture, desolate and how things have disappeared from. So this was the very big milestone for the lab. I was responsible for the quench bypass switch. This shows the picture of this very large 77 millimeter hockey puck diodes that basically they're used to protect the magnets. And this is the aerial view of the picture of this facility just before shutdown. These pictures are, I think I've taken this picture. This is a small piece of the string test. These bus bars or the wires are capable of 500 ampere each, so continuous current. The power supply control room. And the string test took place on here. This is where half cell magnets, 5 dipole and 1 quadrupole was mounted. 100 yards, and it had a small curvature to it, emulating the final ring. Okay, the control room for 7,000 ampere power supply. And this is where the cryogenics, this is the coolant and nitrogen and helium. That's how we feed it to the ring, to the magnets. Voltage control monitor system, we see also quench protection system. This was designed, part of my responsibility. I was designing this stuff. Again, these are some of the stuff that I did back then. Technology, of course, was no surface mount back then. Everything leaded, but it worked. And a lot of wires in the back of this instrumentation rack. And again, some more of that. Of course, technology has moved on. This is 30 years ago. We were flashing the ROM by device like that. So a picture of our dipoles inside the ring. And quadrupole. This hockey puck diode under compression. And for detection of the currents, I had to design this transductor, or there's a current probes as we call it these days, but they are made to measure 7,000 amperes. So the core of this was, to have the lowest losses and to give pretty accurate measurement of the current that's going to magnets. Power supply, some of the circuits, the voltage control monitor. And those diodes were placed inside this cylindrical object. These are those hockey puck diodes for magnet protection. One of the colleagues that worked in that program Again, bypass switch, segments of the spool piece. Again, system, and this is the refrigeration or the cryogenics. That's for you compress the liquid helium, gas, helium, and nitrogen into liquid and feed it to the system. Detector at the Fermilab. Some of these were designed to be eventually installed at. So this is the entire string test that was successfully tested in August of '93. 3 months, 4 months after that project was canceled. This one is showing the access shaft for lowering the magnet into the ground, into the tunnel. This shows magnet test lab again. Here is a long 6-hour video. Those who wanted to watch, it will show you the all this debate that was going in the Congress to cancel. These are the large inductors that was designed at the time in Soviet Union that became Russia. It was for collider power supply filtering. So you can see the size. I'm standing next to one of these inductors. A part of the tunnel that was, for the LINAC. Cryogenics containers here. And refrigeration of the cryogenics compressors. Part of the tunnel again, magnets. Me again here, and then so on. Again, dismantle the dipole magnet.
A look at the.
All right. So where is it leading in today? Accelerators. There are still many accelerators everywhere. Of course, the focus is in CERN right now. That's in Switzerland. And this is just showing that all the active accelerator. This shows interaction proton, p-bar, we call it, antiproton, proton, positron, and antiproton. By the way, to make antiproton, which is opposite of proton, is extremely difficult, very, very costly, very expensive. These are some of the names for these accelerators, that colliders that are around the world. I will bypass that one. And let's go through this one. These are not really important. So 20 years after that, they found out this 135-acre campus for SSC had become a prime spot for thieves and drug parties. Every building had been broken into, stripped of anything that could be used or sold for scrap. Left behind were holes in the ceiling, graffiti tag walls, and remains of multiple alcohol and drug parties. So 20 years later, a company called Magna Land came in 2012, and I guess they purchased this thing from the Department of Energy. That was the owner of the US government, and they renovated. So some of these magnets that is still there, they're all corroded and rusted. Some of the signs outside the facility. And finally, why did it fail? I think it was the inability to get foreign sources and foreign funding. When the machine was designed, or the conceptual idea was Japan, Russia, India, and some European countries giving some funds, financial and also human resources, but that never happened. And that was probably one of the major reasons why this thing failed. Of course, the price of the cost of the collider constantly kept increasing. A lot of design concepts were not sufficient, so they were reviewed. And also, it was an election year. There was a lot of resistance in the Congress for spending money on these programs like so. And of course, that all led to this end of this. So that's the end of my marathon talk, and this I apologize. I had to skip through so much, and I have also slight cold, and my voice is completely preventing me from able to really speak clearly. But it is what's going on, and it was historically a big program. It was a big ticket, a very costly, but also very interesting program. that basically never happened. 4 years, and they spent over $2 billion and many costly things afterwards to fill these access shaft, and also to transport some of the equipment. They had procured a lot of high dollar devices and magnets and so forth, but I really have no idea what happened to it. Some of it probably was left in the tunnel, some were taken to different national labs. But what happened to the United States, I think, to speak with, they lost the edge in building this type of technology, and many benefits came from projects like this. Spin-offs from building projects like this required advances in engineering, and also in that basically would have driven many things far ahead of where we are today. However, most of the physicists and engineers working in this facility, they went to CERN in Switzerland, and they probably are part of those who still are alive. I think majority of these people were older than me. They're probably not alive anymore, but those who are still alive, they worked at CERN, and they are part of this LHC program. Again, I thank you for your patience. I apologize
Well,
again.
thank you, Cyrus. That was really interesting.